We're going to be looking at here some of the practice problems for rotational kinematics. These are sitting in the HP11N underscore Trinity underscore Corona notes. These are three pretty straightforward problems that have to do with the first five videos of the rotation that are in the YouTube page. And this shouldn't take us long to do. If we are prudent and kind of go through it, and have our best friend kind of sitting with us, we should finish this up right real quick. So our first problem here, number 2.4, it is asking us, it says the radius of the tires on your car is, should say R, 0.33 meters. You drive 1,600 meters in a straight line, and what is the angular displacement of a point on the outer rim of the tire around the center of the tire during this trip? So we're looking for an angular displacement here. And remember, an angular displacement is a theta. Assuming the tire rotates in a counterclockwise direction, so it'll be positive. So what they're basically asking us here in this problem is, if I have 1,600 meters as a straight line, how many times did my car tire rotate around? And if we think about this, this car tire is circular, but if I unrolled it, it would go some amount of distance. And if I unrolled it again, it would go some amount of distance. And I kept unrolling the tire over and over. How far would it go? And we're basically asking, how many times would you unroll it, an angular displacement, in comparison to this linear distance here? Now, if we're given a linear distance in S, or some people like to write this as an X, and this is an R, this is just a conversion problem. We know that a linear distance is just equal to an angle times the radial distance of that circle or that angle you're going through, because in your geometry classes, this is just a circumference of a circle. Circumference equals 2 pi, or 1 complete revolution, times the radius. So all we're doing here in this problem is we are rearranging this equation, S equals theta times R, and solving for theta. We're saying theta equals S over R. And with this equation here, our linear distance is actually the 1,600 meters. That's an actual distance that we can travel. So we can say here that our 1,600 meters we have needs to just be divided by the radius of our wheel. And our radius of the wheel is that 0.33 meters. So we'll divide here by 0.33 meters because we're dividing by a decimal. Our number is going to be bigger here. And when we take 1,600 divided by 0.3333, just like multiplying by 3, we get something around 4,800. Now, if you're looking at this and you're like, well, what are the units of that, Mr. Botzer? The meters have divided each other away. What's left? Well, remember that when we're looking at angular quantities, an angular displacement has a distance, so to speak, of radians. It's not a physical unit because a radian doesn't tell you how large of a circle you are, but it does tell you how far around or how much of an angle you've gone through. So we have an answer of radians here of 4,800, okay? And we use that as a placeholder in the world of physics. So that's how we do this first problem. It's just a linear to angular conversion. For our next problem, we are looking at a CD rotating clockwise at 31 radians per second. Now, radians per second, radians is that placeholder of a distance, but it's per seconds here. So this is an angular velocity. What we want to know is, what is the angular acceleration? So we're looking for an alpha here. What would the angular acceleration be if it is going to stop in 28 radians? So this is a slightly larger problem here. In this problem, we have an initial angular velocity of 31. We're looking for an alpha. We're bringing the CD to a stop. And this means that our final angular velocity is a 0. And we're doing it in an angular displacement of theta. So if we think back to our best friend, and if we think back to that video and some of the ones we've seen, we have 1, 2, 3 pieces of information With that, we can solve for the fourth. Remember, out of the 5 things you have, thetas, initial angular velocity, final angular velocity, alphas, or times, if you ever have 3 of those, in this case we do, 1, 2, 3, you can solve for the fourth here. We just need to pick the correct equation. If we take a look at the best friend, oops, what about this? Right here. Take a look at this. We know we can't use equation number 1 because we have an acceleration. So we're stuck using equations 2, 3, 4, or 5. Well, if I have 2 omegas and a theta and I want alpha, the only equation that will work is equation 5r right here. So if we go back and we use equation 5r is the final angular velocity squared equals the initial value squared plus 2 alpha times theta. In this way, all we need to do here is solve for alpha. We'll first subtract by the omega I squared, bring that over to the other side, so that we have the final angular velocity squared minus the initial squared. That will equal 2 alpha theta. And now we'll just divide each side by 2 theta. And remember, that's the entire quantity that comes over, because this in the numerator needs to be subtracted first. So this gives us our final answer that alpha can be found by taking the final velocity angularly squared minus the initial squared divided by 2 theta. It's important to recognize here that you need to square each of these values before you subtract them. This is different than if you were to write this, because if you wrote this, remember, you're actually foiling terms there. You'd actually have 2 terms that exist, and you'd have to FOIL around. So we're not doing that. We are squaring them and then subtracting them. We talked about that earlier on in the year, so make sure you do that there. When we do this, though, when we plug in our values for this problem, our final is a 0, so 0 squared is 0, minus, and then we're going to have the initial value of 31 squared. So in our numerator, we're going to have negative 961 radians per second. In our denominator, we're going to have 2 times the 28 radians, or 56 radians. Oops, this is actually going to be radians squared per second squared. When we divide those, one of the radians is going to go away, which gives us our final answer of negative 17 we'll just round up to 2 radians per second squared as our final answer there. And that makes sense because if we think back to linear acceleration earlier in the year, linear acceleration was meters per second squared. When we do angular accelerations, we need to have the meters placeholder radians per second squared. And that's what we have right there. So we feel good about that problem. For our third problem here, this can actually be done in a few different ways, 2 of them at least. So we'll kind of split this problem up into 2 ways here. And what we have is we have a rotating water pump. And the way this water pump works is it takes water in from one side of it, spins it around, and then the water is ejected from the other side. So if the pump has a radius of 0.12 meters, so let's kind of draw this first. We've got a water pump here. It has some radius of 0.12 meters. And this water that comes through it, it gets gathered on one side, and then it spins around or something, and then the water is ejected somewhere else. That's what's going on. Now, we know that radius. We know it accelerates at this rate, and if it's accelerating, this is an alpha right here, an angular acceleration. And it's traveling, or it's doing this for 9 seconds, which is a time. What we want to know is how fast will the water be traveling when it leaves the pump. And this is not an omega. This is actually a linear velocity. These terms we had here, this alpha, This alpha is an angular quantity. So at some point here, we're going to have to transition from an angular quantity to a linear quantity. So the two ways we can do this, and we'll just kind of split this down the middle, is if we take a look at this, we could start this problem by taking this acceleration and switching it into a linear quantity. This right now is an angular quantity, but we could turn it into a linear quantity. We could say that the linear acceleration equals an alpha, the angular acceleration, multiplied by the radius, which we have, 0.12. So we could find that. We could say it's 30.5 rads per second squared multiplied by 0.12 meters. When we do this, we would find that our acceleration, 30.5 times 0.12, would equal 3.66 meters per second squared. The radian is just a placeholder. The meters go into place there. Now, if we wanted to find a velocity at that point, all we would have to do is say, look, if it starts from rest and it accelerates for 9 seconds and I have an acceleration, well, that means I have three things here. I know that the initial linear velocity is 0. I know the acceleration is there. And I know a time is 9 seconds. That's 3 of the 5 things. So I just need to go to the best friend, figure out what I would pick. And it turns out what you would pick is this equation. VF equals VI plus A times T. Well, our initial velocity here is 0, so who cares? And then all we need to do is multiply the 3.66 meters per second squared times the 9 seconds. And that will give us the final velocity when it is expelled or ejected. So 3.66 times 9 gives us a value of 32.94, and that's going to be meters per second. So that's one way we could solve this problem. Another way we can solve the problem is very similar. Instead of doing the angular to linear conversion first, we're going to do this part at the bottom right here first, and then we're going to do the angular conversion. So what we'd actually start with, if we wanted to do this just kind of in reverse order, is we would say, look, I know that initially my angular velocity is 0. I know my angular acceleration is the 30.5 rads per second squared, and I know my time equals 9 seconds. What is the final angular velocity? Well, we've got 1, 2, 3 things. You can go find the fourth. And we just use that same equation that we used at the very end here, but only we'd be putting in omegas instead of v's. We could say that omega f equals omega I plus alpha t. Omega I is 0, so when we add the 30.5 times 9 seconds here, and that's rads per second squared, one of the seconds go away, and we get that the final omega here is equal to, whatever 30.5 times 9 is. 274.5. And that's radians per seconds. Now, if we just want to convert from an angular quantity to a linear quantity, we know that a velocity is just equal to an angular quantity times a radius. So we know that radius, this is just what we did before. We can say that this is going to be 274.5. 274.5 radians per second times the 0.33 meters. That radians here is just a placeholder for the meters, so it's going to go away. And we're going to get a final answer here of whatever 274.5 is divided by 3. Whoops, hold on. 274.5 times 0.33333. Something went wonk there. What went wonk? Did I type something in wrong initially? I think I did. 30.5 times 9 gives me a final I'm getting 91. Why am I getting something weird? Oh, dang it. This isn't 0.33. This is 0.12. Ugh. 274.5 times 0.12 gives me 32.94. I was getting an answer of 90 some, and I'm like, what is going on? That doesn't make any sense. So we see that in both of these ways, our answers will be the same. I was getting different answers for a while. It was very confusing. That's because this is the radial value, which was 0.12. So make sure you're using the right number, kids. If you mess something up, you might have used the wrong numbers there. So, yeah. And that's the two ways you can do this last problem. So nothing too crazy there. Just two ways to look at it. If you want to do angular to linear first and then find the components, you could do that. Or you could find the components and then switch it over. So, but in the end though, we have all three of the problems for our first practice set completed. It wasn't too bad. Didn't take us that long. Hopefully you try these out beforehand, and maybe if you got stuck, this helped you out. But with that, you've solved it. Congratulations. Way to go. Keep taking a look at the Google Classroom for more things, and keep checking these YouTube videos out for more content. Have a good one. Adios.